Okay, let's look at how we use the product rule to differentiate a function that is a product of two other functions. So we need to remember the formula. So if I want to find the derivative, so if I want d by dx of some functions u and v, so that any two functions, then it's v times u dash plus u times v dash, so vuv. All right, so if we have a look at an example here, I need to change this equation into something I can differentiate. So I'm going to call it y equal to 5x plus 1, and the other one is going to be 6x minus 1 to the power of a half. So I need to change that square root. Now, very important, I need to call one function u and the other function v, okay, because that helps me keep track of the order. So to differentiate, I want to find dy on dx. So the product rule says I need to take the first function, which is v. So the first function is just 6x minus 1 to the power of a half. So we don't do anything to it. Then I need to multiply that by the derivative of u. So u is 5x plus 1, and the derivative of 5x plus 1 is just 5. Okay, now we add u. So u is this 5x plus 1, and then we want to get the derivative of v. So v is 6x minus 1 to the power of a half. We can't use the power rule on this. This is a function in a function. So what we need to do is use the chain rule. So the chain rule says we differentiate the outside. So just pretend that this is all now one thing. So we multiply by the power. So the power here is a half. Then we need to reduce the power of this thing by 1. So we'll get minus a half. And then we need to multiply by the derivative of this inside function. This inside function is 6x minus 1, and the derivative of 6x minus 1 is just 6. And now we can just tidy up. Right? So we can rewrite this as 5 times the square root of 6x minus 1 if we want, or we could leave it to the power of a half, it doesn't matter. And then plus, we've got a half times 6, which is 3, so we have 3 times 5x plus 1. And then we have the 6x minus 1 to the power of negative a half. So that's moving it down to the denominator. And again, we can write this, if we want, as the square root. Okay, so there we've differentiated our equation. Okay, so it's important that we keep track of the functions, and that we remember when we're differentiating each of the functions separately that we might have to employ other differentiating techniques that we've looked at before. Okay, and up to now, that's just the chain rule. Okay, let's look at where we would use differentiation. So differentiation, remember the whole point of finding the derivative is the gradient function. It's a function that describes gradient. And if we wanted to find points where the gradient is 0, we would need to find a gradient function for that. Alternatively, you could be asked where are the stationary points, and we know the stationary points are where the gradient is equal to 0. So here we have a function y equal to x plus 2 squared and 2x minus 5 cubed. Now we could use the binomial expansion, expand these out, collect like terms, and then differentiate using the product or the power rule, but that would be very long and tedious. So what we need to do is we need to first of all give our functions a name. So I'll call this u and I'll call this v. Right? So if I want to differentiate some function in terms of u and v, we know it's just vuv. Okay. So we take v, whatever v is, in this case it's 2x minus 5 cubed, and we multiply it by the derivative of u. So we need to use the chain rule here because this is a function in a function. So we multiply down by the power, and then we reduce the power by 1, so it becomes 1. And then we multiply by the derivative of the inside function. Now fortunately the inside function is just x plus 2, and the derivative of x is 1, and the derivative of 2 is 0, so here we have just 1. So we don't even have to write it if we don't want. Okay, then we're going to take u, and we're going to multiply now by the derivative of v, so v dash. Okay, So again, we need to use the power rule. So we'll multiply down by the power. Sorry, not the power rule, the chain rule and the power rule. And then we will reduce the power by 1. So 3 goes to 2. And then we need to multiply by the derivative of this inside function. Now this inside function is 2x minus 5. And the derivative of that is 2. And from here, we can just tidy things up. So I'm going to have out the front 2, and then I'll have x plus 2, and then 2x minus 5 cubed. And then I'm going to add 6 times x plus 2 squared and 2x minus 5 squared. Now I need to find when the x-coordinates when the gradient is 0. So I've just found something that's called the gradient function, dy by dx. And I need to set this equal to 0. And when I do that, I'm going to have to solve by factorizing. So it's probably in my best interest to try and factorize these two terms. So I can see I have a common factor of x plus 2, and I also have a common factor of 2x minus 5. Actually 2 squared. So what I'm going to do is I'm going to pull out a 2, because this 2 can also be factorized out. And then I'm going to pull out x plus 2, and then 2x minus 5 squared. And what will be left over is going to be 1 lot of 2x minus 5. And 3 times 1 lot of x plus 2. Right, we'll just tidy up that other bracket. So I'm just going to add these terms together. So 2x plus 3x gives me 5x, and negative 5 plus 6 is going to give me plus 1. Okay, so now it's factorized and ready. So this is my gradient function, and I want to know at what x coordinates this gradient function is equal to 0. So we're going to set it equal to 0. So we'll say when dy by dx is equal to 0, so when the gradient function is equal to 0, then 2x plus 2, 2x minus 5 squared, 5x plus 1, this must be equal to 0. And if that's equal to 0, then we can see that x can be negative 2, or x can be 5 over 2, or x could be minus 1 over 5. So those are 3 possible solutions to this. So at these 3 points, the gradient is 0. In other words, these are the turning points of this graph.